All right, so this is the part 2 of the mathematical background for CryoEM single particle reconstruction. And what I'm going to do is I'm going to draw from what we did for random variables in the part 1 and use that to create models for the noise in CryoEM images, talk about their spectra, and say a little bit about the signal in the images. So let me just begin by recalling what we did last time. So we defined random variables by saying that we have an experiment and we repeatedly perform the experiment. And each time we perform the experiment, we make a number of measurements. And these measurements then turn out to be not the same when you repeat the experiment. And when that happens, we say that the measurements are described by joint random variables, one random variable per measurement. And by the way, I want to introduce some new terminology as well. So if x and y are joint random variables describing, say, these two columns of numbers, then as a pair, we will just say that that pair is a single random variable, but it's a multivariate random variable. So that's just terminology. And of course, when we call something a random variable, we have a probability density function for it. And each value of the random variable we say is a sample whose probability density is given by this function p of xy. And it turns out that for this lecture, it's going to be really important for us to distinguish between the random variables and their samples. So random variables represent the entire set of values that that variable can take. So that's infinitely many numbers in this case. A sample of the random variable is simply one set of numbers that you get in a specific experiment. And the way I'm going to distinguish between the random variable and its sample is simply by using the bold font for the random variable and just the ordinary font for xy. So that's the convention I'm going to adopt for this lecture. So our goal in this lecture is to use our understanding of random variables to create a model for noisy images. CryoEM images are noisy, and we need a model for the noise in order to do good single particle reconstruction. And the reason we use random variables for noisy images is that we think of noise as random. And what our model is going to do is it's going to capture the main characteristics of noise that we see in CryoEM images. And then later, in a later lecture, we'll use this model to actually design a single particle reconstruction algorithm. All right, so what's a noisy image? Well, let's begin by just asking what's an image. As far as we are concerned, a digital image is just an array of numbers. So in this case, it happens to be an m by m array of numbers. And the entire array, we're going to denote by I. So I is a single image, an entire array. And the ijth element of that image is a single number. And if we want to denote that number, we either denote it by using the subscript I comma j or by writing I bracket I comma j. I is the row index and j is the column index. So Iij refers to the jth column in the ith row. And for an image, Iij, that one element, is just a single number. This element, by the way, is called a pixel. A pixel is a short form for picture element. So we say that this image has m by m pixels or m square pixels, and the ijth pixel has a value I of ij. So in a noisy image, a simple model for a noisy image is that the ijth pixel has a value which is the underlying signal plus some noise that corrupts that value of the signal. And what we want to say is that the signal is a deterministic quantity, which means if you were to repeat the experiment, in principle, S stays the same, but N now changes from experiment to experiment. And what we now want to do is we want to ask if this noisy part, the part that changes from experiment to experiment, is in fact, if you want to model that as a random number, then what kind of a simple model can we create for it that's going to capture most of the relevant properties of noise in a single pixel and the correlation of noise in 2 pixels. So that's the model that we're interested in developing. And so here's the most commonly used model for image noise. So if you focus on a pixel ij, then the noise in that pixel we're going to say is a random variable because it changes from experiment to experiment. And we'll assume that Nij has a Gaussian density with 0 mean and a variance sigma squared. So we saw in the last lecture that a Gaussian density looks like this. And because it has a 0 mean, the numerator in the exponent is just Nij squared. So I also want to point out that what this formula says is that the probability of a sample, so this is not bold-faced like this. So this is not a random variable. This is a sample of noise. And the probability density of that sample is simply given by this formula. So this model tells us the randomness of a pixel of noise in a single pixel. And we're also interested in whether noise in 2 different pixels is correlated. And that correlation is specified or measured by what's called the autocorrelation function of noise. So the autocorrelation function of noise is simply the correlation between 2 pixels of noise, the first pixel at index I1, J1, so in the I1th row in the J1th column. The second pixel is at I2, J2, so somewhere out here. And we simply measure the correlation between those 2 random variables. And because these random variables we assumed are 0 mean, the correlation is just the mean, the average over all infinite samples of the noise at I1, J1 and the noise at I2, J2. And of course, this number that we calculate, the correlation of the noise between these 2 pixels, you can think of as a function of the location of the first pixel and the location of the second pixel. So this function captures all possible correlations between pairs of pixels in that image. So the autocorrelation function of noise then tells us the extent of correlation between 2 pixels. Now very often for actual image noise, for experimentally observed image noise, this function turns out only to depend on the displacement between the 2 pixels. So it only depends on I1 minus I2 and J1 minus J2. So we write the autocorrelation function simply as a function of delta I being I1 minus I2 and delta J. And to simplify this notation, we just say that the autocorrelation function is a function of I and J. These are not the row and indices in the image. These are simply the differences between row and column indices in the image. So any noise that has this property where the autocorrelation function only depends on the difference between a pair of locations is called stationary noise. So essentially our image noise model is that noise in any pixel has a Gaussian density and that noise is stationary. It has the same autocorrelation for a given displacement anywhere in the image. Okay, and now it's going to be really important for the next few slides that we distinguish between random variables and samples of random variables. So far everything I've defined is in terms of random variables. So at location ij, noise is a random variable, and the correlation function is the mean of the product of 2 random variables. Of course, we don't get to observe a random variable. We only get to observe a sample of the random variable. So if I have a noisy image where Nij is a sample from that random variable, I can calculate the sample autocorrelation by taking a mean over the set of samples of noise I have in this image, instead of taking a mean over all infinite possible samples, which I don't have access to. So this sample autocorrelation function, in some sense, is an approximation of the exact autocorrelation function. And this distinction between the real autocorrelation function and the sample autocorrelation function is going to be really important pretty soon. Okay, so here's an example of what all of this means. So this is a little simulation I did where I'm generating a noisy image. So there is no signal in this image. At every pixel, all I have is noise. And the way I generated noise is by assuming that my autocorrelation function looks like this. So the center of this spike is 0, 0. So this is where the center of the spike is the value of the autocorrelation function when I is 0, j is 0. And as I increase I move along the x-axis, the autocorrelation function drops off pretty quickly. And it does the same thing along y. And all that means is if I take any pixel here, then pixels in its immediate neighborhood are highly correlated to that original pixel, both along the x-axis, y-axis, and in fact in any direction in the image. And the amount of correlation between two pixels is exactly the same, even for different points in the image, because this is stationary noise. So this is the exact autocorrelation function that I used to generate the image. But now if I take this specific sample image where each pixel has a sample of noise from its density, and I calculate its sample autocorrelation function, I get this. And you can see that the central spike is similar to this, but there is a lot of variation in the background. And in fact, even within the spike is not exactly similar to this. There are some small changes as well. But nevertheless, this seems like a good approximation to this, but they're not the same function. Okay, so once you have the autocorrelation function of noise, you can take the amplitude of its Fourier transform. And so here's the autocorrelation function I had on the previous slide. And the amplitude of its Fourier transform looks like this. And that amplitude is called the spectrum of noise. And of course, because the autocorrelation function is two-dimensional, the Fourier transform is also two-dimensional. And so the Fourier transform is a function of two frequencies, one along the x and one along the y. And the important property of the spectrum is that, intuitively speaking, the value of this spectrum at the x and y frequencies is roughly the amount of noise power at those frequencies. So in this particular case, it tells you that this noise has a lot of power in the low frequencies, and then the power drops off and in fact goes to 0 at high frequencies. Okay, and here again, we have to distinguish between the real definition of the spectrum, which uses the true autocorrelation function given random variables, with the spectrum that you calculate using a single image, which is the sample autocorrelation function. So if you took the true autocorrelation function, took its Fourier transform, and took the magnitude of that Fourier transform, you would get the real spectrum. This is the definition. But in practice, what you're going to do is take the sample image, calculate its sample autocorrelation function, take the magnitude of its Fourier transform. And the question is, how is this related to that? So we know this looks like a decent approximation to that, but what's the relation of this to that? And that's shown here for that example I had on the previous slide. So again, that's the noisy image, the true autocorrelation, the sample autocorrelation, and now the true spectrum, which is the magnitude of its Fourier transform, and the sample spectrum, which is the magnitude of this Fourier transform. And now you can appreciate the difference between the something that's calculated using random variables and samples of random variables. So although the autocorrelation functions look similar to each other, their spectra look quite different. And if you're going to use the image spectrum as a model for the true spectrum, you might want to think about maybe smoothing this up so you get something similar to that. Okay. With that, I think we can introduce a terminology that's used very often in modeling noise, which is this idea of white noise. So white noise is simply noise in an image where every pixel is completely uncorrelated with every other pixel. The noise at every pixel is completely uncorrelated with noise at any other pixel. The autocorrelation function, when you have that condition, is simply a large spike at 0 and then 0 everywhere else. And if you take its Fourier transform, then the magnitude of that Fourier transform turns out to be a completely constant function. And that's why it's called white. So if you think of this roughly the frequency as color, then this has all of the colors. So in some sense, it looks white. And that's why this is called white noise. The important part is that the autocorrelation function is a spike, and its spectrum is completely flat. Okay, so the next aspect of the spectrum of noise has to do with what happens to the spectrum of noise when you filter a noisy image. So let's take an image that just has noise in it. And let's assume that it has a spectrum that looks like this. If I now filter that image, filter that noisy image with a filter whose impulse response or template is Hij, and let's say the magnitude squared of that filter's frequency response looks like this, then it turns out that the filtered image, which is noisy, also has a spectrum. And this spectrum is related to the original spectrum and the filter spectrum simply by a product. So its value at any point is the value of the original spectrum multiplied by the magnitude squared of the filter that you're filtering that noise with. And a very good example of this in electron microscopy is the presence of what is called Thon rings. And this is a simulation of Thon rings. And the idea is quite simple. Let's say you begin with a sheet of amorphous graphite. And let's assume, at least as an approximation, that that amorphous graphite has a spectrum that is flat. Now, in reality, it's not going to be exactly flat, so it's going to fall off a little bit. But at least conceptually, let's think of it as being flat. As maybe an approximation to the reality. If you now put this graphite plate in a microscope and take an image, the image you get is going to be this graphite plate convolved with the contrast transfer function of the microscope. So this is the contrast transfer function in the frequency domain, in the Fourier domain. So this is h of omega. And I don't know if you can see the limits here on the z-axis, but the contrast transfer function goes between +1 and -1, and it's radially symmetric. So you have an image which is which is samples from a random variable where the samples are uncorrelated. You convolve it with this filter, and here's the image you observed. So using what we had on the previous slide, we know that the observed image is going to have a spectrum, which is the spectrum of the original amorphous graphite sample multiplied by the magnitude squared of the CTF. And so if I take the output, which is this filtered image, and I look at the magnitude of its Fourier transform, what I get are a bunch of rings, and these rings are called Thon rings. And what these rings are, because this is a flat function, what these rings are simply the square of this function. So remember, this function goes between plus and minus. So if you start at the center and you go along the x-axis, you can see that there are 3 positive peaks, and then correspondingly 3 negative peaks. So if you start from here and walk all the way out, you can see that there's 1, 2, 3, 4, 5, 6 peaks. So these 6 peaks correspond to the positive and negative peaks because we now have to square the magnitude of h of omega. So all minus ones also appear as plus ones appear as plus ones, and you get 6 peaks. So Thon rings tell you something about what the contrast transfer function of your microscope is. And it's a direct consequence of this property of noise, of stationary noise, the fact that its spectrum, just the spectrum of filtered noise, is just the spectrum of original noise multiplied by the magnitude square of the filter. Okay, so now that we've described what noise looks like, what its probability distribution looks like, we can start asking what happens in an image when you have a signal as well as noise. And when you have a signal plus noise and you assume that the signal is deterministic, that it does not change from sample to sample, then the probability density of any given pixel still remains Gaussian, has the same variance as before, but all that happens is that the mean shifts from 0, so noise at 0 mean, to actually having a mean that's equal to the signal. So that's the probability density of a single pixel. And if you assume that the noise is white, which is that the noise is not correlated for 2 different pixels, then the probability of the entire image simply becomes a product of the probabilities of every pixel. That gets more complicated when noise is not white, but we're not going to deal with the complicated case in the course of this lectures. We'll just always assume noise is white. So this then tells you what the probability density is of the entire image, given that the signal is deterministic and noise is random. And that's the model we're going to use in a subsequent lecture to actually derive a reconstruction algorithm. Okay, so here's the summary of what we've done so far. So we thought of images as noise, images where the content of any pixel was a sum of the signal and the noise. We model noise as being random, and a random noise in an image, if it is stationary, has an autocorrelation function and a spectrum, and you can approximate both by taking a single sample of that noise and looking at the sample autocorrelation and the sample spectrum. So I want to make one last point before we move on to the next lecture, and that is, so far we assume that the signal is deterministic. And what I want to know is that really true? If I were to repeat my experiment and say I did not have any noise, would I get back the exact same number? And it turns out that that's not quite true. So here's an example of what an electron microscope camera does. So there are essentially 2 generations of cameras that we have to deal with. The older generation is a fiber optic camera, and the newer generation is a direct electron counting camera. So let's look at the fiber optic camera first. So the idea behind these cameras is that you have a thin film that is a scintillator. And the property of the scintillator is that when an electron comes down the microscope and hits that film, there is a finite spot that begins to glow, which means it emits light or photons, and that light then propagates through this fiber optic channel and hits a CCD camera. And what you record then is the light that hits the CCD camera. Now, because the scintillation diameter is larger than the actual pixel size in your CCD camera, every time you get an electron hitting this, what you end up with is a blurred response because a whole set of photons come down and hit that CCD camera. Also, the conversion of electrons into photons is a random process. So if you were to repeat the experiment with a second electron hitting the scintillator at the exact same point, you would not get the exact same set of numbers in each of these pixels. So even the signal, it turns out, is random. But if you have a lot of signals, if you have a whole bunch of electrons hitting the scintillator more or less at the same point, what you would end up measuring is the mean over that randomness, and that mean is a deterministic signal. So that's what we usually assume. We assume that what we have is a case where we have a reasonable number of electrons so that the signal we get is a deterministic signal. So the situation then improves quite a bit if you use what's called a direct electron counting camera. And this is the kind of camera that exists now in most high-resolution modern electron microscopes. And these cameras directly detect the electrons. So there is no scintillator, there's no fiber optics involved. The camera has a bunch of pixels, and when an incoming electron hits a detector, roughly the detector measures the amount of charge that is now present at that pixel. Now, in the first generation of these electron counting cameras, it turns out that when the electron hits the pixel, there's a lot of scattering of secondary electrons, and so neighboring pixels also have some charge in them. And so you get essentially a blurred response, even though it's only a single electron that's hitting the camera. In more modern versions of the camera, there's an underlying algorithm which detects the amount of charge in all of the pixels and then collects all that charge and associates it with the pixel that has the highest charge in it. And the assumption being that's the pixel that the electron actually hit. So what you end up with is an image that is much sharper than the image that you get with this and the image that you get with the fiber optic camera. But again, this is a random process, because if you were to repeat the experiment with the electron hitting the same point, the secondary electrons might have a slightly different distribution, and it is possible that the eventual allocation of charge to a pixel might end up being in some other pixel. But again, if you have lots of electrons, what you will end up measuring is the mean of all of that, and that mean is a deterministic signal. So although the signal is random in electron microscopy, we will continue to model it as being deterministic. So the noise will be random, the signal will be deterministic. Okay, that's all I have for this lecture. Now that we have all of the stuff in place to actually describe the formation of an image starting from a particle, we can then work our way towards actually developing algorithms for particle reconstruction. Okay. Thank you.